Known to medieval Europe as Al-Hazm, the scientists from Iraq conducted an experiment that we're going to try and recreate here at Star and Shadow on the 8th of March. So while people in medieval Europe were quibbling about the salvation of their souls and other nonsense like that, he was busy devoting his time to what he called a doctrine whose matter was sensible and whose form was rational. Later, in Cairo, he had to pretend that he was mad to avoid getting killed, but now he's got a crater on the moon named after him, and so it's partly due to this experiment and we're going to try and recreate it. Al-Hazm was born in Basra in what's now Iraq, and he worked at the court in Persia where various refugees had fled Athens to continue working on the old Greek ideas of science and the old theories that we see in Plato, that for example the light projects some kind of active beam and that comes back to us, and that's what light is, and also the idea that the atomists had, which is that all particles leave behind some kind of tiny husk on our eye, and that's what you see when you witness the reflection of a cat's eye, for example. These kind of ideas were disproved by Al-Hazm's experiment, which showed that these husks could not all fit through the hole in his camera obscura at the same time and spread out again to produce the image, and also the beam could not fit through the hole at the same time. It had to be a different theory that was accurate. It was a sunny day. It was Renaissance Italy in Florence, and this guy Brunelleschi stood in front of the cathedral, which he would later in life design the vault of, the new dome for, and he looked across at the piazza. We're going to try and redo this demonstration. Basically, he painted really carefully, using perspective lines, the scene that they could see in front of them. But he got them to look in a mirror and then hold the painting blocking their face but with a peephole, so they're looking through the painting at a mirror showing the painting, and by holding this painting in the mirror in that position they could trick themselves into seeing what they thought was the real piazza in his painting, and by doing this he proved the perspective lines about how distance points can be kind of lined up. And that had not been done before. Before that time it was all about the symbolism of things. Things were big if they were important, they were small if they were not important, and location told a story. At that point he worked out that spatial geometry could be demonstrated, and that's how light worked as well, how he saw light.
So where the laser beam should be going is there.
In a straight line.
Yeah, so I push this in and it comes out of there.
Yeah.
So as it goes in, it's been bent by the change from going into air into glass, and then when it comes out from going to glass into air, it bends it again and ends up over there. That's diffraction. So if we had light going in that was made up of more than one wavelength, each of the different wavelengths would be bent by a different amount, and we'd actually see a spectrum over here. So we're going to try and do that.
The famous image of Newton is of him in a darkened room with a single beam of light coming through a small aperture and then going through a prism. And what Newton did was Newton would then separate the white light into the colorific rays, and then he could recombine them again back into the white rays with another prism. And so Newton was analysing light into its least parts, and he believed that these parts were different sizes. So there was red-sized molecules, or not molecules, there was red-sized particles, there was green-sized, etc. And so he believed that our sensations of colour were to be understood as our subjective response to the objective reality of corpuscular size. That's what Newton thought. But Newton was wrong, and Goethe worked it out. He got a prism, he tested what Newton said, and he realised that actually something else was happening as well, that Newton's theories could not explain. What Goethe saw in the prism was not the same light effects as he should have seen according to Newton's theories. We're going to try and do a colour shadows experiment at the cinema to try and show what he was seeing and why he realised Newton was wrong. Basically, if you get two lights, one's white and one's red, they shine against the wall and cross in the middle, so you get kind of an X shape of the beams. If you stick something in the middle of those beams where they meet, you should create a shadow in each of the lights. So the white light will have a shadow in it and the red light will have a shadow in it as well. You should not, from that red light, be able to get colours that are not red in its shadow. It should only have these red particles coming through it. However, if you do the experiment, you should hopefully discover that you see green colours in the shadow of the red light. How? That's another question.
So light is made up of a wave, and sometimes made up of particles. But in this case, we're just talking about waves. And we know this because of the general nature of how waves act. If you have two waves that hit each other, they interfere with one another. So if you have a peak of one wave hitting a trough of another wave, they cancel each other out, thus having no wave. If you have a peak of one wave hitting a peak of another wave, you end up with a double peak, so a large wave. And this gives you what's called an interference pattern. So if we look at light, and we have shined light through a couple of slits, each slit then acts as its own source of light. So the light from those slits will then interact with the light from the other slit, and you'll see that when the trough of one hits the peak of another one, you cancel each other out and you get no light. So you end up with a band on a screen that's dark.
The diffraction shows that it's a wave. Interference shows that it's a wave. And it's only when you start looking into, let's say, the atomic spectra, where the light from a star is split through a prism, and rather than seeing a continuous wavefront, so lots of different wavelengths, but as a continuum, there were discrete values of wavelength. So it's in trying to understand this spectra led to the understanding of atomic spectra, so where the light comes from. And the light comes from electrons changing energy levels in atoms. And then the electrons in the energy levels can only have certain values, they're quantized. And because they're quantized, one change in energy level corresponds to one energy. So as the wax is heated up, because there's heat there, the energy levels, or electrons inside, are moving between levels, so giving off photons. It just so happens that those photons that are giving off the energy there corresponds to red light or orangey light.
Just so happens, or is that because it's low energy?
Well, it gives it too because it's low energy. But this is the problem. You want to use atomic spectra to show that it's quantized. It's a quantum, but the problem is that the measurement for that shows it's a wave.